All right, so this is the review for chapter 3, talking about bond polarity. Oh, I don't think I shared the screen. Okay, here we go. All right, so we're on bond polarity. So now we're trying to figure out, we know the shape of a molecule, but then we're trying to figure out, is this molecule polar or not? And when you think about polarity, I always think about the Earth's poles, right? They're far away from one another, they're different, or the north and south pole of a magnet. That's kind of a good one to compare it to, because if you flip-flop your magnets, then they repel each other instead of being attracted to each other. So if you think about polarity in that way, you can think about that for a molecule. So polarity of a molecule is determined by if a part of the molecule is partially positive and then another part of the molecule is partially negative. Okay, so we can indicate this in many different ways, but the reason why you have polarity, the reason why part of the molecule is a little bit positive, part of the molecule is a little bit negative, is because not all atoms are created equal. Each atom has its own unique ability to pull electrons away from other atoms. And so we say that that's its electronegativity. This is its ability to attract attract electrons, right? And so if we go to our best friend, we have this fantastic little electronegativity value table. And fluorine right here, fluorine is the most electronegative element. And I call this fluorine the floozy, because fluorine can attract electrons from any element. It will take electrons from anyone. So if you're just trying to think about that in terms of the periodic table, just keep in mind that fluorine is that most electronegative. It wants electrons the most. So the closer the element is to fluorine, the more electronegative it is. And there are different ways to indicate electronegativity. You can indicate electronegativity with these partial signs. This is partially positive. This is partially negative. So it's saying that fluorine here is stealing the electrons from hydrogen. So the electrons are spending more time with fluorine than they are with hydrogen. And so the arrow points to more electronegative element in the bond. So here fluorine's more electronegative, so the arrow is pointing to fluorine. The plus sign over here is on the side of the atom that is partially positive. And so that's why I make that little plus at the end of the arrow. Okay, so we're looking at some elements here and we have their bonds. And so all I did was take this same chart that's in your best friend and I posted it right here. And I went and I said, okay, carbon is 2.5. So I put 2.5. Nitrogen is 3.0. I put 3.0. I just wanted to see, okay, if I look at each individual atom, is one atom more electronegative than another? Well, sure, nitrogen here is more negative. So whichever atom is more negative, those electrons are going to be like, hey, I'm going to hang out with the one that's more negative. And so we make this little arrow and we say the nitrogen's more negative. And you could do nitrogen's more negative, carbon's a little bit positive. And so we should say that they're not sharing those electrons equally. The electrons are hanging out more with nitrogen than they are with carbon. So we say that this is polar covalent. Okay, the next one, carbon and chlorine. So if I go and find those electronegativity values, I see that chlorine has an electronegativity of 3.0. So this is more negative than the electronegativity of carbon. And so the electrons are going to go hang out with chlorine and not so much with carbon. So carbon's going to become partially positive, chlorine partially negative. Remember, electrons are negatively charged. So whoever they hang out with more is going to become more negative. Whoever they hang out with less is going to become a little bit more positive. So this would again be polar covalent. Okay, oxygen and hydrogens. What's more electronegative? That's my oxygen, more negative. And so my electrons are going to go hang out with oxygen and not so much with hydrogen. Makes oxygen partially negative, hydrogen partially positive, and that makes it, again, polar covalent. All right, now D, I have two hydrogen atoms. They have exactly the same electronegativity. So there's not one that's more electronegative than another. So the electrons will be shared equally. Electrons shared equally. Therefore, we call this a non-polar covalent bond. And we don't draw anything because nobody's partially positive, nobody's partially negative. They're equally sharing the electrons. Now, here's where it gets a little tricky. You have to remember this. There is an electronegativity value between carbon and hydrogen. And I know you want to say, well, carbon's more electronegative, so the electron should spend more time with carbon. And that's true. But the electronegativity difference is so small that we basically say it's about the same electronegativity. And so we say the electrons are shared equally. But that is only for carbon and hydrogen. That is the only time you will have two atoms that are not the same atom where we say that the electrons are shared equally. So if we say the electrons are shared equally, it is non-polar covalent. And we'll see why that's really important later. All right, nitrogen and hydrogen. Nitrogen is more electronegative, so more E negative. That means that electrons are going to go hang out with nitrogen more, less with hydrogen. Nitrogen is going to be partially negative, hydrogen partially positive. Okay, so then it says indicate polarity. We did that. Okay, write the Lewis structure of ammonia. I'm assuming you know how to do that. Show the polarity of the bonds between the nitrogen and the hydrogen on the structure you drew, either using partial charges or the dipole moment arrow. So what you have to do is you first have to evaluate each individual bond. So I'm going to look at every single bond between hydrogen and nitrogen. Who's closer to fluorine the floozy? Nitrogen is closer to fluorine the floozy, so the electrons are going to go to that more electronegative nitrogen. Same thing. So what's going to end up happening is that each hydrogen becomes partially positive, while the nitrogen becomes partially negative. And if we wanted to look at the overall, this whole molecule, because each of these arrows that I've drawn are just for a bond. But if I want to do this for the whole molecule, I need to pick a side of the molecule that's more negative. Well, like up here is more negative, down here is more positive, right? So basically what I'm going to do is I'm going to draw an arrow. Try not to lift my pen. That's a terrible looking arrow. Terrible. Okay. So if I do this, okay, I can just take that arrow and push it off to the side and say, okay, that's my dipole moment. We typically don't draw a dipole moment on top of the molecule just because so much is going on. But we're just saying that up here is partially positive, down here, up here is partially negative, down here is partially positive. And that's all we're saying. Okay. What's the molecular shape? Well, all we have to do is our handy dandy best friend and say we have 4 electron groups. 3 of them are outer atoms, 1's a lone pair, so it is pyramidal. Right. Draw the overall dipole moment. Oh, we did this. Okay, we did this. Yeah. All right. I was just ahead of the game. We're going to do the same thing for water. So when we draw water, I should have had this already drawn. Sorry, y'all. 1, 2, 3, 4. Okay. So now I need to know, do I have polar bonds? Well, oxygen and hydrogen, yeah, they're different. Oxygen's more negative, so I'm going to have these two different bonds that have some differences, and so that's going to make my hydrogen partially positive and then my oxygen partially negative. And so the question is, do we have a dipole that's going on in water? Do we have one part of the molecule that's partially negative and one part that's partially positive? Well, of course we do. Up here, this is my negative portion. Down here, this is my positive portion. So if I were to draw a dipole arrow, I would draw it basically like that. Because if I brought that over my molecule, I would just be saying, I would be saying that the top is where the arrow points, that's my negative, and the bottom down here is the positive. But we just leave it on the side. Okay, so yes, water has a dipole. Yes. Okay, draw the Lewis structure for carbon dioxide. We did this before, and that's not. And then each oxygen has 2 lone pairs. Okay, so now, if I draw my bond arrows, I know, okay, oxygen's more electronegative than carbon. Oxygen's more electronegative than carbon. But if you kind of think about this in terms of vectors, if you've ever taken a physics or something like that, I know if you looked above at water, right? If I have these 2 arrows that are going like this, if I added them together, I'm going to get an arrow that kind of goes in between. But what if I kind of have the opposite, where I have 1 arrow going in one direction and 1 arrow going in the other direction, and it's the same intensity? Then basically, you have to think about like the carbon being pulled on the left and the carbon being pulled on the right. If it's pulled equally on the left as it is on the right, the carbon's not going to move. It's not actually going to have a dipole moment. So carbon dioxide has no dipole moment, even though it has polar bonds. And the reason is it has no dipole moment because the molecule is symmetric. So if I had any other element, like if I had, I don't know, let's see, where's my electronegativity table? If I had something like, let's say, sulfur instead of oxygen on one of these, if I put a sulfur here, then this would become polar, but it does not. It just has oxygen. It's an equal pull on either side of the carbon. So because the molecule is symmetric, there's no dipole, even though we have polar bonds. So the shape of this molecule, I have 2 electron groups, 2 outer atoms, no lone pairs. It is linear. So although carbon dioxide has polar bonds, it is a non-polar molecule. So non-polar means no dipole. No dipole, non-polar, same thing. So provide an explanation, and we said that's because the molecule is symmetric. It has to do with the shape, and it has to do with them both being oxygens on either side of the carbon. All right, so let's look at some more. Draw the structure for carbon tetrachloride. So carbon, Cl, then we got to put lone pairs. Okay, so draw the structure. We did that. Show the polarity of the bonds. Okay, so let's show our bond polarity. Who's more electronegative? Chlorines are more electronegative, more electronegative, more electronegative, more electronegative. So basically what's happening is that this chlorine is getting pulled in 4 different directions, but it's all 4 directions that oppose one another equally. Because remember, this bond angle was 109 degrees. Every single bond angle is 109 degrees. So our molecule bonds have polarity. Yes, we have polar bonds. So that's the question. Do we have polar bonds? And in order to be a polar molecule, the answer has to be yes, okay? So then you have to look at the molecule. Is the molecule, and then there are two options. It's either symmetric or not symmetric. If it is not symmetric, then yes, we have a polar molecule. If it's symmetric, then the answer is no. Okay, so do we have a symmetric molecule? Yeah, this molecule is symmetric. It's all the same. It's tetrahedral because we know we have 4 electron groups, 4 atoms, no lone pairs, so we know that we are tetrahedral. So do we have a polar molecule? What is the overall dipole moment for this molecule? This molecule has none, right? It has no overall dipole moment because this is a symmetric molecule. It doesn't look like it in 2 dimensions, but we're going to do some stuff in class and you're going to be able to see it in 3 dimensions. So why do some molecules that have polar bonds and yet are nonpolar molecules, whereas other molecules like water and ammonia have polar bonds and are polar molecules? So what you have to do is you must have polar bonds and an asymmetric shape. So you need 2 things. So using a dipole moment, indicate the overall molecular polarity, and then tell if it's polar or nonpolar. We're not going to do D. D is a little tricky, and I'm not going to do that to y'all. So let's just come down and let's do the other ones. A, HBr. So if I have hydrogen and I have bromine, 4, 5, 6, 7, right? So what I'm going to end up with is, and you really probably did it better than me, and you did that, and you turn this into a single bond, right? Okay, so now, who's more electronegative, bromine or hydrogen? Bromine's much closer to fluorine, the floozy, so we have a bond polarity, and I guess I should really put that closer, right on top of the bond. That's my bond polarity, which makes the hydrogen partially positive, the bromine partially negative. And then if I want to give an overall dipole moment, do I have one? Yes, I do. And it is a polar covalent molecule because it's, even though it's linear, I don't have 2 of the same thing. So this is an asymmetric molecule. If I drew a line here, does the left look like the right? No. So it's asymmetric, which makes it a polar molecule. Okay, B, OCS. So this is carbon that's bonded to an oxygen and a sulfur. Oxygen and sulfur are in the same group, so they have the same number of valence electrons. So this structure is the same as CO2. So now, do we have polar bonds? Well, oxygen, if you looked on your periodic, on your best friend, has an electronegativity of 3.5. Carbon has 2.5. Sulfur has 2.5. So these 2, carbon and sulfur, are the same. So there's no polarity there. But these 2 are different. And oxygen's more negative. So we're going to point to the oxygen. Okay, so now we have a polar bond. Do we have a polar molecule? Yes, we do. We have an overall dipole moment. Yep, that looks like this, where we have a partially positive side and a partially negative side. And so this is polar covalent, right? Polar covalent. All right, C, CH3F. Okay, so carbon's my central atom. I'll have a fluorine and 3 hydrogens. Okay, so here's my structure. Remember my carbon-hydrogen bonds, those are all non-polar bonds, but my fluorine-carbon is not. Fluorine's more negative, so I'm going to give it a polar arrow, and then I'm going to say, okay, is this molecule symmetric or asymmetric? Well, it's asymmetric, right? Even though we have that tetrahedral shape, it's still asymmetric because I have 1 fluorine and the rest are hydrogens. So this molecule has an overall dipole moment that looks like this. So this one is polar covalent. Okay. All right, now this last one is just a tad tricky. CH2Br2. So if I go ahead and draw this, I have a carbon, and I know I'm going to have 4 things attached to my carbon. When you draw like this, if you have 2 things and 2 things attached to a central carbon, you have to put them as next door neighbors. So the bromines have to be next door to each other, and the hydrogens have to be next door to each other. You cannot do this. You cannot do BRH, BRH, because this doesn't actually exist. And I'll show you in 3 dimensions in class. Okay, so my bromine, I need to give it electrons. All right, so who's more electronegative? Well, our bromine is more electronegative. And so each of these bromines is going to be like partially negative. My carbon's going to be partially positive. And so now basically what I have to do is to combine these 2 dipole arrows here. And so if I were to do that, it would kind of end up being somewhere in the middle, right? And so now I just take that and move it. Oh, I forgot. Oh, that's terrible. Let me? No. Okay. So then I'm just going to draw it on the side. Maybe? Just get the eraser. Okay. Is that I'm going to draw it to where it kind of looks like this. Right? It kind of depends on how you drew it, however your direction goes. But if you have these 2 little arrows that are kind of doing this, then your big arrow has to be in the middle. So the big arrow would look like that. So, okay. So that is it for our polarity. Hope that helped.